Hello folks. So in this video we're going to start off our unit on trigonometry and graphing them specifically. So you've seen trigonometry and the trig functions in geometry, but you probably didn't graph them. So that's what we're going to do now here in Algebra 2, and then you're going to see it again in pre-calc. So I just want to use this time now to get a little head start on that. So this video is going to focus on just reminding us about what the sine and cosine and then tangent are, and also remind us how we get these values. Okay, so start with some definitions, and all these sine and cosine and tangent, they all come from right triangles. So we'll draw a right triangle. So let's pretend that's our right triangle there. I'm gonna just pick one of the angles, and usually you just pick one of the angles and then everything is calculated for that angle. Here's what I mean. This angle, I'm gonna call it theta. Oopsies, sorry about that. So this angle, that symbol that I just drew, is the Greek letter theta. I believe it's lowercase the way I've drawn it. So this theta, Theta, and that's just a, I guess, universal indicator that you're talking about an angle. If that is the angle we're interested in, then we have different vocab terms for the different sides. So the hypotenuse is always just the hypotenuse. That's what makes it a right triangle. The side, or the leg that is next to the angle, we're going to call this leg, I'll draw an orange. That orange leg is the adjacent leg. Adjacent. And the purple leg here, that is the opposite leg. If we agree on these definitions then of what is adjacent, opposite, and what the hypotenuse is, then here's how we define sine, cosine, and eventually tangent. So sine, spelled just S-I-N, of what angle? The angle we're looking at is theta. So sine of theta is equal to, well, opposite over hypotenuse. And you might have heard the phrase SOHCAHTOA. So SOH is opposite, or sine equals opposite over hypotenuse. So it's opposite over hypotenuse. Cosine of theta is equal to the adjacent leg over hypotenuse. Adjacent over hypotenuse. And the last one is tangent, and that is equal to the opposite leg over the adjacent leg. So every side of this right triangle has two trig functions that use it. So for example, the hypotenuse shows up in sine and cosine, but not tangent. The opposite leg shows up in sine and tangent, but not in cosine. And then the last one, the adjacent leg, shows up in cosine and tangent, but not sine. And so every leg is used in two of the functions. Okay. And the way you would say these, I was saying it earlier, but I would say tangent of theta, whatever theta is. Quick example of what this would look like, because I said opposite and adjacent and hypotenuse. Remember that these trig functions, the values that they put out is just a ratio, just a number. A ratio, i.e. a number. So an example of this would be, let's pretend I have let's say I have a 3, 4, 5 triangle. So this side will be 3, 4, 5. I'm using 3, 4, 5 triangle because I know it's a right angle, or I know it's a right triangle, excuse me. This would simply mean that sine of theta is equal to, well, it's the opposite over hypotenuse. So the opposite leg in this case is, actually let's write this down, opposite over hypotenuse. So that would be 4 over 5. Cosine of theta would be equal to adjacent over hypotenuse, which is 3/5. And lastly, tangent of theta is equal to opposite over adjacent, which in this case is 4 over 5. Another way that people think about tangent is, if you imagine this being a line on your coordinate plane here. You could think, oops, that's really messy. Let's draw it this way. You could think of this 3 and the 4, the two legs, as a slope triangle following this line here, and I'll draw the line in black. This would mean that your 3 is essentially your delta x, and your 4 is equal to your delta y. If that's the case, then this is delta y over delta x, which is the slope, rise over run. And so really, tangent of theta is another way of identifying the slope of this line with a certain angle off the horizontal. That is actually going to come up later as well, so hang on to that for now. One more thing I should point out before we move on is the importance that these values, sine, cosine, and tangent, are all ratios. And so what I mean they're ratios is I don't care, or the function is not going to matter how big the triangle actually is. That ratio, so long as it's the same angle, is always going to be the same. Here's what I mean by this. I don't know what the value of this theta is in a 3, 4, 5 triangle. Not exactly, but take a look at this triangle. So I'm going to call this theta 1, the first one. If I draw a new triangle, I'm going to draw it significantly bigger, and this is going to be a 6, 8, 10 right triangle. So we can use Pythagorean theorem just to confirm that this actually is a right triangle. So 6 squared plus 8 squared does equal 10 squared. But also, these two triangles are similar. I simply doubled every side length. If you remember from geometry, then that would mean that these two triangles are similar. So that's what this squiggly line means, is they're similar. And therefore their angles should be preserved. And so this angle right here, theta 2, is actually the same angle as theta 1. So because they are similar, theta 1 equals theta 2. And let's look at sine, cosine, and tangent for this new angle. Sine of theta 2 is going to be, well, look, the opposite case is now 8, and the hypotenuse is 10. So this is going to be 8 over 10, which when I simplify it, comes down to 4/5. And so it doesn't actually matter how big your triangle is. All that really matters is what the angle is, because that angle is going to determine how long the sides are anyway, and thus the ratio will actually be the same. Okay. Next thing I wanted to talk about was actually getting some value. So I don't actually know what theta is here, so this would not be very helpful if I was trying to maybe use the angle to find the side lengths, which is kind of the purpose of trigonometry. So there are a couple significant angles that you just see so often that it's worth remembering. I don't want to just tell you what they are, though. It's for you to memorize, because that would defeat the purpose of this whole video. So let's actually show why they are what they are. The first significant angle I want to talk about is 45 degrees. And I don't know if significant angle is like the universal phrase, but that's just what I call them, because they are significant. They show up a lot. Common angles, maybe. 45 degrees. And I want to find their sine, cosine, and tangent. Actually, we'll just focus on sine and cosine for now. And we'll show later why I don't actually need to remember tangent at all. So let's draw this triangle. I'm always going to draw my angle in the bottom left corner, by the way. So, or my theta. So there's always a right angle, because remember this trig stuff depends on right angles. And this angle down here is theta. In this case, theta equals 45 degrees. And for these next couple, well, for now to the end of the video, we're going to have to rely on our knowledge of geometry. So bear with me here. If this angle is 45 degrees, then since the angles within the triangle have to add up to 180, well, this is 45, this is 90, I believe then that the last missing angle has to also be 45. If that is the case, then this is actually not just a triangle with two common angles, it actually has two common side lengths. And if I turn it upside down, not upside down, on its side, or on its hypotenuse, this might look a little bit more familiar. I have 45 and 45. And so these two legs must be the same length. Alrighty, so let's label them again. So I'm just going to label them my hypotenuse, opposite leg here, and my adjacent leg right there. This would mean then that since adjacent and hypotenuse are both the same, I can just call them, let's say x. Okay, call them x and x. With a little bit of Pythagorean theorem, we could actually see that the hypotenuse is equal to x times the square root of 2. And I didn't show the algebra step, but you might want to take a minute, and if you're not sure of that, convince yourself that that is the case, because it is the case. Okay, so now we have that. Let's take a look. Sine of theta, or let's say sine of 45 then, degrees. It's important to put degrees here because later you're going to see another unit that you can measure angles in. So in this case, we're using degrees. So sine of 45 degrees would be, let's see, opposite over hypotenuse. So in that case, the opposite leg is x, and the hypotenuse is x root 2, or x times root 2. Cosine of 45 degrees is adjacent over hypotenuse, but remember that adjacent and hypotenuse are actually the same length in a 45, 45, 90 triangle. And therefore, it's still just going to be x divided by x root 2. Lastly, we have tangent of 45 degrees, and that's just going to equal opposite over adjacent, or x over x. We can clean all these up and just be left with, well, scooch over here, 1 over root 2, 1 over root 2, and 1 here. What does this mean? It means that no matter how big your triangle is, this triangle could be giant, like this. And this could be, as long as I know what the angle is, so that's 45 degrees, then I know that the ratio of this adjacent side to the hypotenuse is always going to be equal to 1 divided by root 2. And likewise, the ratio of the adjacent side, oh sorry, that's the opposite side. Although that's totally fine in a 45, 45, 90. So this will be the adjacent side. And likewise, the cosine of that 45 degree angle is going to be 1 over root 2, and tangent is always going to be 1. Which also makes sense if we think of it in terms of the slope, because the slope of this line, if this is, that's really messy, if this is 45 degrees, goes right down the middle, this is the line y equals 1x, by the way. Now, usually we don't see sine and cosine of 45 degrees as 1 over root 2. The more common way you're going to see it is rationalize. So I don't want that irrational number in the denominator. And so we're going to multiply it by root 2 over root 2. And so this simplifies to root 2 divided by 2. So these you're going to want to hang on to. Again, if you remember sine and cosine, you're good. Tangent, you don't have to remember, but it just works out nice and easy. Okay, the next one we're going to talk about is the 30 degree angle and the 60 degree angle. And we're going to talk about them together because they are related, and you'll see pretty quickly why. So we have 30 and 60 degrees. So let's draw first a 30 degree angle. So I'm going to draw, it's going to look something like this. And here's my, oops. I'll do it the other way. I'll start with my 60 degree angle because it helps to draw it vertically. 60 degree angle. And notice, if I have 60 degrees and 90 degrees used already, the missing angle has to be 30 degrees. Alrighty, so let's pretend that this angle, the 60 degree, is my theta for now. Well, how the heck can I figure out how long these three side lengths are? Well, here's where the geometry trick comes in, because the way that this is going to work out is if I think of this as half of an equilateral triangle. So I'm going to finish that equilateral triangle right here. in an equilateral triangle, you have a total angle at the top here would be 60 degrees. And so that leftover piece should be 30. And this piece, right, this angle down here will also be 60. If that's the case, then in this equilateral triangle, let's just call the side lengths x. So I'll call this side x, x, and this whole thing down here will be x. The reason this is helpful now is because I can actually figure out this missing shorter side. That altitude right there actually splits that bottom base in half because this is an isosceles triangle. Therefore, this piece has to be x over 2. And so with this side, x over 2. And now that you have two sides of a right triangle, you can use Pythagorean theorem to get this missing side. So I'll call that question mark. That question mark there, I guess it would be the height. We'll use h. I like to use question mark, but some people don't. So let's call it h. I know that h would be the square root of x squared minus x over 2 squared. Again, this is just using Pythagorean theorem. Let's work this out. So h will equal square root of, let's see, this will be x squared minus x squared over 4. I'm going to combine these like terms by getting a common denominator. So this will be 4x squared over 4. So h would be equal to the square root of 3x squared over 4. I can take the square root of x, and I can take the square root of 4. Sorry, the square root of x squared and the square root of 4. So this, but I can't take the square root of 3. So this will come out to x over 2 times the square root of 3. And you're most commonly going to see this like so. The square root of 3 over 2 times x. So that's what h is. If I draw this now, so let's go back to what we were originally looking at. Here's my 60-degree angle. Theta equals 60 degrees. I now know that this side length is x. The vertical side there would be root 3 over 2. And the short leg is x over 2. Again, the short leg here on the bottom would be the adjacent. The vertical leg would be my opposite. And x itself would be my hypotenuse. So now I know that sine of 60 degrees, oops, look, sorry, 60 degrees is equal to, root 3 over 2 x. And so sine of 60 degrees would be root 3 over 2x divided by x, which, as you can see, simplifies down to square root of 3 divided by 2. Likewise, cosine of 60 degrees is equal to x over 2 divided by x, which simplifies to 1/2. And so that's sine and cosine of 60 degrees. The 30-degree triangle, you notice that the triangle is actually going to look exactly the same, just on its side. So if I split this right here, I'm going to draw that triangle. Just now, here's my 30 degrees, and that's my theta that I'm interested in. That would mean this leftover piece has to be 60 degrees. This picture and this picture are exactly the same. You just turned your head. And so the values of the side lengths are going to be exactly the same, because this would have just come from another equilateral triangle like so. So if I call this side x, then the short leg here would be x over 2, and I'm not going to go through it again, but the long leg would be root 3 over 2, root 3 over 2x. Therefore, sine of 30 degrees would equal, be careful here now, so this angle that we're looking at is the 30-degree angle, and so the opposite would be now x over 2 divided by x, which is 1/2. Cosine of 60 degrees would be the root 3 over 2x divided by x. So that's root 3 over 2. So really, as long as you can visualize what a 30, 60, 90 triangle looks like, and remember that it is simply half of an equilateral triangle, then you'll be able to figure out or pull out these trig values. So sine of 60 degrees is always going to be root 3 over 2, and cosine of 60 degrees, is 1/2. And likewise, sine of 30 degrees is 1/2, and cosine of 60 degrees is root 3 over 2.